This diagram shows the gravitational attraction at different points due to the Earth. As you can see, the arrows are pointing toward the center, and the arrows get longer as you move closer to the surface of the Earth because the gravitational field strength is getting stronger. Here's the moon. Okay, so you can see the arrows for this one are also pointing towards, the red arrows are pointing toward the center of the moon, and they're getting stronger as you get closer, but they're not as strong as the one from the Earth because the Earth's got a much bigger mass. To find the resultant gravitational field strength, you would have to add these two vectors at each point vectorially. They'd give a resultant like this. Okay, so let's look at that one more time. So you've got the individual attraction from each point due to the two different objects, attract them towards center. And then when you add them up, you get a force resultant gravitational field pattern that looks a bit like this. What we're going to look at is how the force changes as along a line that's joining the center of these two objects. The diagram shows a stationary space probe between the Earth and the Moon. Describe and explain the subsequent motion of the space probe. So as you can see, that space probe is d/3 from the Earth and 2d/3 from the Moon. The distance to the Moon is twice as large. So the force of attraction from the Earth is going to be much bigger than the force of attraction from the Moon. The one reason being the distance, like I mentioned, is twice the distance to the Moon. So if distance increases, the gravitational attraction decreases, inverse square law. And also the Moon has a much smaller mass. The mass of the Moon is 1/81 the mass of the Earth. So we can figure out roughly how much bigger the size of the force from attraction from the Earth is. And the resultant force is going to be towards the left, so it's actually going to accelerate towards the left. So let's do some numbers. So if we use the equation, so the mass, we're going to compare the force from the Earth to the force from the Moon. The mass of the Moon is 1/81, and the distance to the Moon is 2 times bigger, but that's at the bottom there, and also it's going to get squared. It's actually times 4. So 1/81 divided by 4 is actually going to be 1/324. So the force from the Earth, from the Moon, sorry, is 1/324, the force from the Earth. Okay, what about if we move the space probe halfway between them? So the traction from the Earth is still going to be bigger than the traction from the Moon. The reason being, even though the distances are the same, it's the mass that has the effect now. So if we use the equation, the mass from the Moon is 1/81 compared to the mass of the Earth. So the force from the Moon is going to be 1/81 compared to the mass, the force from the Earth there. The distance don't matter because it's the same for both. So the resultant force is still towards the left and it will accelerate towards the left. At a point between the Earth and the Moon, the gravitational field strength is 0. The x is the distance to this point from the Earth. Find x in terms of v. So there's going to be a point where the gravitational attraction from the Earth and the gravitational attraction from the Moon is going to be equal and opposite in opposite directions. So it will cancel out to give you 0 resultant attraction. This point is going to be closer to the Moon than it is to the Earth because the Moon's mass is much smaller, so it's going to have to be much closer to the Moon to get that same attraction. So we can use this equation to figure out the ratio, okay, and use that to figure out x. So we know the mass of the Moon is 1/81 compared to the mass of the Earth, but we want the gravitational attraction to be at this some point to be the same. So what do we need to do with the r squared at the bottom? Well, the r squared at the bottom is going to have to be 1/81 as well, so it cancels out with the 1/81 at the top there. For the r squared to be 1/81, the r needs to be root 1/81, which is actually 1/9. So because if we do 1/9 squared, that actually becomes 1/81, which cancels out with the 1 at the top to give the same gravitational attraction. So we know the distance from the Moon is going to have to be a ninth the distance from the Earth. So we have x and 1/9x. If we add them together, that should give you e, which is the distance from the center of one to the center of the other. Now we can solve this to find what x is in terms of d, but those two numbers, you can't add them right now because they have the same denominator. So I'm going to multiply the left one by n at the top and n at the bottom. Okay, so it's 9/9, same as x. Okay, and then that becomes 10/9x, and then just rearranging, I get 9/10 d. So what this means is that the distance from the Earth has to be 9 times bigger than the distance from the Moon. Okay, what about if the space probe is towards the right of the Moon and the Earth like this? In this example, we want to actually calculate the gravitational force on the space probe and not just use ratios here. So in this case, we're going to have attraction from the Moon and from the Earth and they're going to add up together because they're both pointing towards the left here. So to make a bigger force, we've got the mass of the space probe, we've got the mass of the moon. We can find the mass of the Earth from the data sheet, or it's going to be given to us. We've got the distance from the center of the moon to the space probe and the distance from the center of Earth to the moon. Let's use Newton's law of gravitation. Let's figure out the force from the moon first. So the gravitational constant times the mass of the moon times the mass of the space probe divided by the distance. Now it's 8 times 10 to the 6 kilometers, so times that by 3 to turn into meters, and then don't forget to square it. Okay, that gives us the force from the moon. And let's figure out the force from the Earth now. So the gravitational constant times the mass of the Earth, again, that's from your data sheet there, and then times the mass of the space probe divided by the distance. Now the distance is going to be the sum of the distance from the Earth to the moon and then from the moon to the space probe, because you have to add those up from the center of the Earth to the space probe there. And of course, I've turned that into meters as well by times each one by 10 to the 3 and then adding them. Okay, don't forget to square this as well. And if you got those two together and then you add them up, you get the resultant force of attraction on the space probe there. Okay, the diagram shows the Earth and the Moon. Complete the graph below to show how the gravitational field strength varies with distance from the center of the Earth along the line AB. Take right as positive and left as negative. Okay, so we're going from A to B and we'll look at how the gravitational field strength changes. So if you're on the left of the Earth there at a point A, it's going to have an attraction towards the Earth. And so that force is towards the right, so it's going to be positive. And that force gets bigger as you get closer to the Earth. So it's going to look a bit like this. Okay, the force getting bigger. It's almost an inverse square relationship there. Okay, so, and you can draw the line like this. And at the surface, as we know, it's going to be 9.81. Okay, and then on the other side, the gravitational attraction is going to be towards the left, again towards the center of the moon. And that's going to be the case for quite a large distance here, because the moon, we know the mass of the moon is much bigger. So because it's towards the left, that means there's going to be a negative force, and it's going to get weaker as you move further away. It's going to look a bit like this. It's going to get weaker as you move further away from the Earth like this. Okay, on now, as we get closer to the moon, however, the attraction is going to be towards the moon like this. But the attraction won't be as big even on the surface of the moon, because we know the moon has a much smaller mass. So actually the gravitational field on the surface is sixth the gravitational field on the surface of the Earth. But that force is towards the right, so that should be positive now. So it's going to look a bit like this. So if we join this up, we get a field strength that varies like this. As you can see, there's some point in between where the gravitational field strength was 0, and we found where that point was a minute ago. Okay, now on the right-hand side of the moon, it's going to be an attraction towards the moon. So the force is towards the left there, and it's getting weaker the further away you move away from the moon. And so the field strength will vary like this.